Hi there. All right. We are getting ready to go to chapter 2. So today we are going to be talking about matter and just kind of getting over the basics of matter. And, you may have learned a lot of this stuff even in elementary school, but sometimes even what we learned, we don't really know how to distinguish between. So today we're going to be going through a couple different definitions that you want to be able to get good at distinguishing between. For instance, like what's the difference between a compound and a molecule, an atom and an element? Okay, a pure substance and a mixture. So as you go on the journey with me today, let's see if we can figure this stuff out, okay? All right, maybe. Go, yeah, advance. Oh, you're just going slowly right now. It's going, but it's going slowly. Okay, so we need to distinguish between elements and compounds today. Atoms and molecules, another set that we can do. Pure substance and mixtures. And then the properties, composition, and methods of separation for those things. And then we won't actually have to memorize these symbols. Normally we would have to do that, but in this online environment, we're not going to have to memorize those because you can just look those up. Although I would say it's a good thing to look those up or to memorize those, because then it'll save you time. You don't have to look them up a lot of times. You can save a lot of time for that. All right. So what do we already know about elements, compounds, mixtures, and pure substances? Just think about what you have actually learned in the past and think about the difference between them. Like, could you really tell me right now the difference between a pure substance and a compound? Okay. Is a compound a pure substance, or is a compound a mixture because it's made up of more than one thing? So, I mean, you see what I'm saying? Like, some of you guys might feel really confident about it, but some of you guys might be like, yeah, okay, maybe not. So that's what we're going to do. We're going to learn about it today, right? So you probably are now getting a little groggy, and we're going to ungrogify you. What do you know about the difference, or about, atoms and molecules, and what's the difference between those? All right, we're going to go through some of these definition by definition. You probably have these things in your notes already, so let's just talk about it, and if you want to add anything to your notes, you can. Chemistry, study of matter and how it changes, right? So this is what we're finally getting to. This section of our physical science text is about chemistry. We are going to learn how the world works, okay? And that's one of the things that makes chemistry so awesome. Everything is made up of chemicals, all right? It's a study of matter. And almost everything you can think of is going to be matter. So the entire universe is made up of this stuff called chemicals, and we're going to learn more about it, and it's going to make your world amazing. Those of you guys are like, yeah, I don't know, I think English is my favorite subject, or maybe math. And they're going to be like, no, man. After chemistry, you're going to be like, science. Science is my favorite. All right, matter. Anything that has mass and occupies space, right? So it has mass, occupies space, it's matter. And again, what can you think of that's not matter? Well, light, yeah. There are things, but it's not easy to think about things that are not matter because the world, the universe is made up of matter. So we're going to learn about chemistry because chemistry has to do with everything just about. All right, elements. Let's start distinguishing. Okay, is there a difference between an atom and an element? Well, an element is a substance that can't be broken down into simpler substances by chemical means. Well, atoms are kind of like that too, aren't they? Like if I take an atom, I can't break it down into ordinary chemical means. Like if I could go nuclear, I could break it up into smaller pieces, right? But under ordinary chemical means, I cannot break apart an atom, and I cannot break apart the most fundamental part of an element either. Okay, but now if I have a whole bunch of gold, I could take it and I could break apart my parts of my gold, right? But elements are substances that can't be broken down by ordinary chemical means. And so when we think about gold, we could think about a bar of gold. Those are still both the same element. Okay, so let's bring element down all the way to the atomic scale. And now that fundamental atom, that single piece of that element, is going to have the characteristics of that element, right? The smallest particle that has the properties that the element has is an atom. And this comes from the Greek a, right? To cut, and tone to cut, and a, which is not, okay? So in other words, not to cut. So Democritus, who's the guy that coined the term atom, he basically said, I believe that at some point there's going to be a place where you cannot cut anything into half anymore. And so he came up with or coined the term atom, and we still use that today. Now, today we know we can cut it with nuclear means, but under chemical means, we can't cut it. So atom is still just a great word for something you can't cut apart any further. So an atom, you can have an element, and you can have an atom of that element. But I could have two different atoms, they could be different elements, right? And so element and atom are not the same thing. An atom is the smallest piece of a particular element. An element will have a characteristic property depending upon which element you have. Gold is not going to have the same property as mercury, right? These things are going to be different elements, but they might both go down to the atomic level, and you might be able to have an atom of gold and an atom of mercury, right? And so they're not the same thing, but they both can describe not being able to break things down any further. Remember that elements have definite properties. Okay, so they're not going to be changing. In other words, if I have a whole bunch of gold or a little bit of gold, they have the same properties. Okay, good conductor of electricity, for instance, right? They're going to have the same properties. A lot or a little, the element is going to have definite properties. And throughout the little block of gold, all those different atoms of gold are all going to have the same property. Elements, they have either 1, 2, or 3 letter symbols. Only the first letter of any element is capitalized. Okay, so remember that you've got, let's say, H for hydrogen, He for helium. And, we actually don't have any 3-letter symbols right now because we have named all of our elements that we've discovered. Now, a lot of times, throughout the last, decades, we've had 3-letter symbols, which were the Greek numbers, basically, or the Latin numbers. Unum Pentium. And those things would be like 115. Unum Pentium would be the Latin name for 115. Okay, and so we would just use these 3-letter symbols, UUP, to say, oh, well, that's the number 115. Once we come up with a name for it, then we'll do something there. But not right now. We all have just either 1 or 2-letter symbols. Second letter is always lowercase. First letter is always capitalized. Okay? All right. Compound. So that's an element. And the element is a pure substance. A compound is also a pure substance, okay? A compound is made up of atoms of 2 or more different elements. So there's the big thing there. Compounds have 2 or more elements inside them, okay? Different elements. So it might have like a sodium and a chlorine or something like that, right? And that they are joined by chemical bonds. So these are not just mixtures. They're not just hanging out next to each other. They're attached to each other, okay? They're bonded together. Compounds, like elements, also have definite composition, all right? It's going to be the same throughout. If I have a cup of water, the water here is going to be the same as the water there. It's the same composition throughout, okay? So this is water, H2O. You're always going to have this 2-to-1 ratio of hydrogen to oxygen. That's the compound. If I have a different compound, H2O2, hydrogen peroxide, that is going to have a different composition than H2O. But H2O2 will have the same composition throughout itself. Okay, H2O has the same composition throughout itself, but they have different compositions between each other. They're 2 different compounds. Okay, so compounds have properties that are very different from the elements. Classic example you're going to see over and over again, NaNCl make NaCl. Sodium is this reactive metal. You put it in water, it explodes, right? Chlorine is this poisonous gas that, they used in World War I and killed people. You take those 2 very dangerous things, you put them together with some electricity, all of a sudden you have table salt. Sodium chloride, table salt. You can salt your food and eat it. Something that's not harmful to you. And yet you start with these 2 really harmful things, and then all of a sudden it's not harmful because it has very different properties from the original elements that it comes from. That's one of the characteristics of a compound, okay? So, practice, element versus compound. AR, argon, element or compound. Okay, again, you might want to hit pause, pause it. All right, come back. Argon is an element. K, that's potassium, an element. I, okay, I2 in this case, iodine, it's an element. Ki, potassium iodide, oh, that's a compound. All right, so one of those things is a compound. The other ones are elements. These guys, these guys all just have made up of 1 type of element. This is the only one that's made up of 2 types of elements, Ki, okay? All right, let's go on to the next one. Chemical formula. We use chemical formulas to describe compounds and elements, okay? So chemical symbols and numbers. So here's some symbols, here's a number, right? We use these little subscripts. Now that's actually a little bit too big of a 2. It should be a smaller 2 up there. My bad, need to correct that. And it's over and over and over again. But the chemical symbols and numbers indicating the atoms contained in the basic unit of a substance. Okay? And the subscript, like I said, it's that smaller number that you put to the right and below to show the number of atoms. We don't have to write a number 1. Okay? So if it was just CO and there's one C and one O, we don't have to have C1O1. Okay? So if there's just no number there, it means that there's one of them. And so in this case, CO2, it means I have 2 oxygens and 1 carbon. Okay? So how many of each of these atoms do we have? H2O, 2 H's, 1 O. MgCl2, 1 Mg, 2 Cls. BaSO4. Be careful here. Look, we have one element, Ba, barium, another element, sulfur, another element, oxygen. That 4 does not talk about the S or the Ba. The subscripts are only talking about the element that they immediately follow, right? So there are 4 oxygens, 1 sulfur, 1 barium. Na2CO3, 2 sodiums, 1 carbon, 3 oxygens. Ca in parentheses, OH2. Okay, now these parentheses, just like in math, you would kind of distribute the 2 to both the H and the O. So we have calcium, 1, oxygen, 2, hydrogen, 2. Okay, so if you're trying to describe the numbers of elements, that's what those look like. All right, now that was a compound. And compound are made up of 2 different atoms. Molecule. This is 2 or more atoms chemically bound. Does it say different here? No, it doesn't. So the big difference between a compound and a molecule is that a molecule does not have to be made up of different atoms, different elements. Sorry, it has to have more than one atom, but it does not have to be made up of different elements. Okay, so a molecule and a compound are not the same thing. A compound could be a molecule, but a molecule would not necessarily be a compound because a molecule could be an element as well. All right. They can be either elements or compounds. So, for instance, oh, by the way, remember this is different in the text, okay? In your text, they give a different definition to molecule. Do not keep that definition in your notes. Scratch it out. Put this definition in your notes, okay? This is the one we want you to learn. We don't like that text definition. You're like, what? Hey, can you just change the text like that? Yeah, we can. So just change it up. Many other texts have the definition that we use. I don't know why our text does that definition. I've never seen it anywhere else. Maybe it's a mistake. I don't think so. I just don't know what they're thinking. All right, anyway, here we go. So let's practice. H all by itself, just an H. Okay, what's that going to be? Well, is it a compound or a molecule? No, because it's only got one type of atom. Okay, and it's only got one atom. That's the big part there. And so H is an element, and that's the only one that can be here. H2, however, that's still an element, and it's still the same element, but this one can also be a compound because it's made up of 2 atoms, right? 2 or more atoms, chemically bonded. They're bonded. And so that is actually a molecule and an element. Same thing we have here. O is an element. O2 is an element and a molecule. H2O is not an element, but it is a molecule and it is a compound. Molecule because it's made up of 2 or more atoms. Compound because it's made of 2 or more different elements. The H and the O, hydrogen and oxygen, different elements. Cool. All right, so remember a couple other little highlights about compounds. They have definite composition, that the elements are combining in definite ratios, and the properties are different than the properties of the compounds. I wanted to show you the indigo dye as an example. Okay, so here's the indigo dye. It's got 16 carbons, 10 hydrogens, 2 nitrogens, 2 oxygens, and all of these are combined together in a very particular way to create something that has a very particular function. Now, I can take carbon, hydrogen, nitrogen, oxygen, and I can take different arrangements of them, and I can make different substances. And that's the cool thing. Like, if you think of all the different substances that are existing in this world, there are just really mostly about 90 different elements that make up so much of the stuff that we have. Okay, we have on the periodic table 118, but 90 of them are the ones that we typically see making up almost all matter that we deal with, right? And so it's pretty cool. If you arrange these elements in different compounds and different types of arrangements with different numbers and different connections, then you get totally different properties. And that's such a cool thing about chemistry. You know, I forget what it was, but there was like a sweetener that if you could change the location of the one hydrogen in that sweetener, break it off in one pot, put it on another, it becomes like this really deadly poison. What? Yeah. I mean, that's how crazy it is. One little hydrogen, boop, 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 You go from a sweetener to death. All right, cool stuff. All right, so if we look at this, these are all, look, neon, hydrogen, oxygen, chlorine, and phosphorus. These are all elements, yeah, but they're also, some of them are molecules. Good job. Neon is the only one here that's not a molecule. All of these are molecules. Neon is only an atom, and it's an element still, but it's only an atom. So all elements, 4 molecules, 1 atom. Okay? All right. This one, oxygen and hydrogen combined together, they're chemically bonded together. If the atoms are touching each other, which we're seeing here, atoms touching each other, that's the way we're representing their bonding, okay? If they're not touching each other in a model, they're going to be separated out, okay? So this is a compound. Is it a molecule? Yeah, it's a compound and a molecule, right? Molecule because it's got 2 or more different atoms, or sorry, 2 or more atoms. Compound because it's got 2 or more different atoms, right? Okay. Pure substances versus mixtures. Pure substance, any matter that has definite properties. So if I look throughout that whole substance and I zip through there and on that side and over there in that corner, if they're the same properties throughout, that's a pure substance. A mixture is going to have different properties in the different little parts that I look at it in, okay? So elements and compounds are both pure substances. So what's a mixture? A mixture is going to have variable composition. For instance, think about sweet tea versus unsweetened tea. Now, tea is made up of water and a bunch of tea leaves made up of tons of different little chemicals, right? And so if I have sweet tea, that's not going to have the same composition as unsweetened tea because the sweet tea is going to have this other compound called sugar in it. And if I move throughout that tea, if I were on a really, really small scale, like if I were like a molecule and I could move throughout it, I'd find these chunks and pieces of sugar in there, okay? Because that's the sweet part. And so sweet tea does not have the same composition throughout, even though you and I might taste it and it might taste the same everywhere. If we're able to dip into it in small little pieces, think about like a salad. I can dip in and find a cucumber there and a tomato there. It's not the same throughout. So sweet tea is going to be the same thing. You just got to zoom into the atomic level, and now you can be like, oh, there's some sugar and there's a little tea and blah, 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 right? So variable composition in mixtures, whereas it has a consistent composition for pure substances, right? Or definite composition. The properties are similar to the properties of the components. In other words, that sugar still tastes like sugar in that tea. The water part is still going to be wet, right? So these things are going to have properties similar to their original properties. And remember, in compounds, it wasn't that way. Here's a crazy sodium and a crazy chlorine that could be deadly, and all of a sudden, salt, hey, it tastes pretty good. That's not the case here, is it? Here, we've got sugar water, which still tastes like sugar, right? And still is wet like water. They maintain their properties. Mixtures can maintain their properties. I can eat the cucumber and tomato together, but the cucumber still tastes like a cucumber and the tomato still tastes like a tomato. You know what I mean? That's why mixtures are that way. Now, we have 2 different types of mixtures, the homogeneous mixture and the heterogeneous mixture. And the homogeneous mixture is going to be the same throughout. Heterogeneous mixture is going to be different. Now, the tool we're going to use, that I want you to use to determine if something is homogeneous or heterogeneous, is your naked eye. Okay? Because think about it. If we have a microscope that is so good we can take down to the molecular level, then we're going to be able to tell the difference between any mixture. They're all going to be different, right? Oh, well, that sugar atom looks, or sugar molecule looks different than that salt molecule, or not molecule, but compound, form of a unit. But so anyway, we have to use some tool, and I'm going to say use your naked eye. If it looks the same throughout with your naked eye, then we're going to call it homogeneous. If it looks different throughout, you can see little pieces of this and that and the other with your naked eye, then we're going to call it heterogeneous, okay? So we're going to use the naked eye to determine the difference. So flour water, if I take some flour and some water, put them together, flour is going to settle out, and I'm going to have water on top and flour on bottom. Boom, I can see that with my naked eye. Concrete. If you've ever looked closely at concrete, chip it off and look inside, see little pieces of rock in there. You can see difference with your naked eye. Granite. Here's some black flecks and white flecks on my granite countertop, right? That is going to be a heterogeneous mixture. However, homogeneous, brass. Some of you guys like to play instruments, right? And think about your brass, which is made up of copper and zinc. Those things look the same, right? Naked eye, you can't tell the difference between the copper and the zinc. If you had a really amazing microscope, maybe you could. Scanning, tunneling microscope. But no, you can't tell the difference with those with your naked eye. So brass is a homogeneous mixture. But it's a solid. Yeah. It's also a solution. It's interesting to think about this. A solution is synonymous with homogeneous mixture. And Brass, a solid, can be a solution. You can have solid solutions, liquid solutions, gas solutions. Kool-Aid, can you see the little pieces of coloring or sugar that's in the Kool-Aid? No. So that's going to be homogeneous. Salt water, can you see the little pieces of salt? No. Now, if you put a ton of salt in there and it settles to the bottom, then you don't have a homogeneous mixture anymore, do you? Then you would have a heterogeneous mixture because you had so much salt that it couldn't actually dissolve in it anymore. Water and alcohol, you put those together, you don't see the difference between those. Air, no, it's right here. You can't see the difference. All right, here we go. So that's homogeneous versus heterogeneous. A couple other examples. The shirt, okay, is it heterogeneous? Can you see the difference between the cotton fibers and the polyester fibers with your naked eye? Maybe. Maybe. I might argue that this would be homogeneous. I guess I have to look at a shirt that actually looks like that. You might be able to tell the difference because they might look slightly different. Definitely could tell with a microscope, okay? And so we could call that heterogeneous mixture if we were looking at a microscope. We might be like, yeah, I can see the difference, but with your naked eye, I don't know. So I think I might call that homogeneous, but I haven't actually looked at a shirt like that to be sure. Oh, no, not really. Okay. Homogeneous mixture. This one, in this case, is your vinegar, okay, acetic acid, and water. Those are mixed together. That's homogeneous. Here, you've got, oh, well, yeah, your salad for sure, heterogeneous. See the difference in the naked eye. Water, this is a pure substance, right? Water is going to be a compound, although in this case, really, they're just showing you only one type of molecule here. But in reality, the real water that you're drinking, even purified water, is going to have tons of impurities in it. But if you could actually look at the molecular level, you probably would not see this. You'd probably see impurities in there. All right, so let's classify this matter. Okay, let's break it up into those two basic groups. Matter is classified into two groups, pure substances and mixtures. Pure substances come into two categories, elements and compounds. Okay, again, look at the molecular model. Single atoms, okay, in this case, they could have more than one atom, but they'd have to be the same ones touching together, right? And a compound, two different types of atoms. All right, homogeneous mixture versus heterogeneous mixture. Notice the layer. Okay, very important here. In these little molecular models, if it's heterogeneous, you're going to see one layer distinctly separated from the other layer. That's how we have to show you in a model. Okay, if we take these different colors and put them next to each other, then our naked eye isn't going to see that. Okay, so that's going to be homogeneous in that model. We're going to practice that here in a little bit. All right, I thought I'd throw this in there just to make sure you could see. These would be the elements that you would have to memorize. These are the ones that you use commonly. And so these would be ones that would be great to memorize, okay, if you wanted to. Would not be bad. And in fact, I love it when people decide to memorize the entire periodic table and say it or sing it to me, all right, because it's just a lot of fun. So if you do that, I might give you a bonus of some sort. In fact, there are a couple different element songs that are fun to listen to. The periodic table song by ASAP Science and the element song by Tom Lehrer. This one, I think in particular, is really a lot of fun. And so there's some links to that. If you guys want to just do a Google search for those, you'll find those as well. Fun to listen to. This one uses a particular song that you'll be familiar with. It's also, if you guys have done the state song or country song, they use some of those same tunes for that. So it's pretty fun. All right, so miscible versus immiscible. Two types of mixtures that we want to talk about here. Ways of mixing. And really, you could kind of throw in the word mixable and immixable, and it basically would be the same thing. Miscible means that you can mix it, that you can dissolve these liquids into each other. Okay, so if I take alcohol and water, put them in, I can't tell the difference between them. They just all come together. Okay, so for instance, remember, if we had something like this, which has got the alcohol on top, the isopropyl alcohol, and the material, which is salt water on bottom, and we mix those together, two or more liquids that are able to dissolve into each other. Now, we could mix these temporarily, but they always separate back out. Let's look at immiscible. Describes two or more liquids that do not dissolve into each other. Like oil and water. When you put oil and water together, you could mix them up, but they eventually separate back out. Okay, so just like this one is going to mix up, but it's also going to separate back out, right? And so these two substances, the isopropyl alcohol and the salt water, are actually immiscible, you know, because if they were miscible, then they would dissolve into each other, and you wouldn't be able to see these different layers that are occurring. Okay, so immiscible versus miscible. Immiscible, like oil and water in a lava lamp, they are not able to dissolve into each other. And although that looks like it dissolves into itself because it's got that layer in the middle that just looks like clear water still, it doesn't really mix in terms of actually staying dissolved into each other. They separate out. All right, so let's do a little bit of review. Let's see if we can use these models, and let's see if we can figure out what each of these things are. Can you classify them into element, compound, and mixture, and explain why? Hit the pause button, pause it, and here we go. This one is all mixed up, two different types of substances, homogeneous mixture, okay? What are we trying to do? That's a mixture, and it's homogeneous. What about this one? Same type of substance throughout, although you can see some of them seem to be connected and some of them don't. Okay, is it the same element? Yeah, I think we can probably assume that it's the same element, but without color, maybe we don't know. Okay, so in this case, we are going to talk about an element made up of both diatomic and monatomic components. Compound, made up of two different types of elements, right? So two different elements chemically combined, so they're touching each other. So this is a compound, an example of a compound. Here we have this substance and this substance. This is definitely a mixture. And this would be a heterogeneous mixture. We've got an element up here and a compound down here. This element could also be considered a molecule. This compound could be considered a molecule. But we have them separated into two different layers, and so we say heterogeneous mixture. Let's go to our next one. You ready to pause it? Actually, I'm going to give you the next one first. All right, ready? Pause it. And here we go. First one, element, all same type of substance. Second one, compound, chemically combined, two different elements, right? And again, the colors here might help us a little bit more than that last one. And this one, we've got some that are single red ones, and then we've got some red ones that are connected to the blue ones. So here we have a mixture of an element and a compound, right? Homogeneous mixture because they're not separated into different layers on that molecular level. Element, now they're connected, but they are not different types connected, right? So this is a molecule and an element, all right? And then this one is going to be a mixture of two different elements. But what kind of mixture? Homogeneous, right? Because they're not separated into two separate distinct layers. And again, remember the heterogeneous mixtures, if we were going to the molecular point of view, we'd have to show you those different layers. You might not be able to see those different layers, with your naked eye, but here on the molecular level, we definitely, would know that the only way we could call it a heterogeneous mixture is if we had a layer of blue down here and a layer of red up there or something like that. That would be the only way we'd say heterogeneous mixture. Okay, I think we've done what we needed to do. Today, we've talked about classifying matter, and we can now distinguish between elements and compounds, right? Element made up of one type of substance. You can't break it down any further. Compound could be broken down under ordinary chemical means. Elements cannot, right? Compounds are made up of two different types of substance, elements one. Atoms and molecules. Atom is only going to be made up of one thing. A molecule is going to be two or more. So you could have an element that's an atom and an element that's a molecule. It could be the same element. O2, O3, and O are all elements. But O2 and O3 would be molecules, only that O by itself would be considered a single atom. But O2 and O3 would be made up of atoms. They're just combined. Pure substances and mixtures. Remember, we want to be able to distinguish the properties. Pure substances are the same throughout, right? Mixtures are going to have different composition, okay, versus the same composition. Methods of separation. Well, we didn't really talk about that. Let's talk about that real quick. We have a few different ways to separate our mixtures, and one of them might be distillation. Okay, and that would be heating it up and causing it to boil and evaporate off and then recollecting it under a cooler temperature. And you can collect it to different layers of the liquid that way. You could do decantation. That's where you pour off the liquid and the solid stuff stays behind. You could do filtration, where you have like a little filter paper, you pour it in, the filter paper holds the solid stuff and the liquid stuff goes through. Okay, you've got different types of separation that you could do. You could actually just physically, like the salad, I can move my cucumbers there, my tomatoes there, various different types of separation, okay? One of the best ways to separate salt water, for instance, is distillation. Remember that one? I think that one might be on your test. Distillation. All right, and then, yeah, yay, we don't have to memorize those this year, but do it anyway if you want. It's not a bad thing to do. and it's going to help you get through tests and quizzes and stuff like that a lot faster. Definitely needed in chemistry. We're not going to be in quarantine still or doing crazy hybrid stuff in 2 years from now, are we? I sure hope not. So memorize them now. Might as well be cool like that, and then you'll have them for chemistry when you have to memorize 51 of them instead of 33 of them. All right, so there we go. I think we had a good time today, and I think we've learned some more stuff. Maybe some of it was review, maybe some of it was reinforcement, maybe some of it was brand new, but either way, you know more now than you did before, and you're going to be able to use that stuff in your day-to-day life, and by golly, it's just fun. So have a great day. God bless.